Hey friends, this is Ben again. This is an audio for the differential equations class. Here we're going to take a look at some examples where we find out about the eigenvalues of a matrix. Eigen, for some reason I have always been under the impression that that was the German word for first, but it's not. I've been learning a little German lately. And checking, it means own, not as a verb, but rather as the adjective belonging to. And if I look further into translations of it, it uses the notion of inherent. And that captures what we're talking about here. When we refer to an eigenvalue of a matrix, it is a value that is sort of characteristic of the matrix. It tells you something about what's happening with the matrix itself. Okay, so the best thing to do is to show you examples. So, all right, let's see if the iPad is going to cooperate today. Please. There we go. Yep. Yay! It's gonna cooperate. Yay! And as you can see, I've titled today's notes eigen stuff. I know that's a goofy name, but I will use the term eigenvalue, eigenvector, and if you put them together, I will say eigenpair. And if you take the system of them, it is sometimes referred to as an eigenspace. So eigenstuff seemed like a good enough name. All right, so we are going to look at these two eigenpairs here. And we're going to notice that when we have ax equals lambda x, so x is a vector and A is a matrix. And so A has to be square for this to even make sense, right? The lambda is a number, a value. So if ax equals lambda x, that means when you multiply that vector x by A, you get a multiple of the vector, okay? And you have this proviso: the vector can't be zero, okay? Now, the value can be zero, but not the vector, right? So here, for instance, we're going to take the vector 1, 1, 2, 2, and we're going to multiply it by the matrix, or the vector 1, negative 1. So when you dot that column vector with that row there, you can see they're perpendicular, so we get a 0. Same thing happens with the other row. So this is 0 times 1, negative 1. So that's the lambda, and that's the x. Now, you need to spot that if I'd used 2, negative 2, or 3, negative 3, any multiple of it, I would still have gotten the same result. So that is what sort of thing is happening. Here's another eigenvector for it. So I'm going to take 1, 1, 2, 2, and I'm going to multiply it by the vector 1, 2. Okay. So when I do that on top, we're going to dot 1, 1 with 1, 2. You get 1 plus 2 is 3. On the bottom, we'll have 1, 2 dotted with 2, 2. And so you get 2 plus 4 is 6. And that is 3 times 1, 2. So you have a multiple of the same vector that you had there. So that is the notion that we're trying to get across here, is what an eigenvalue and an eigenvector are, okay? So let me see, does my next example, no, my next example goes to a 3 by 3. All right, so what I want to do here is to go ahead and erase what we just worked out there. And what I want to do is to show you how you figure out what the eigenvalues and eigenvectors are. So keeping in mind that ax needs to be equal to lambda x, if we wrote ax minus lambda x equals 0, because lambda is a value, it doesn't make sense to factor out and have, I should not have done that way. Okay, it doesn't make sense to factor out and say a minus lambda times the x equals 0. But if you want to have something that you can subtract and is the same size, we'll just talk about the appropriately sized square identity matrix. Okay? So if you have a solution to a matrix times x equals 0, and the x in question is not the 0 vector, then that means that the thing you're multiplying by, that matrix A minus lambda I, needs to be not invertible. Okay? Because if it were invertible, then you would take and multiply the inverse on both sides and get that your x vector has to be equal to 0, the 0 vector. So if we know that A minus lambda I is not invertible, that means its determinant has got to be 0. Okay, that was one of our theorems from the previous section. So that means if I took A, which was 1, 1, 2, 2, I'll leave some space there, and I subtracted lambda from it on the diagonal, that determinant needs to turn out to be 0. And that determinant is 1 minus lambda times 2 minus lambda. Oh, darn it. I have put myself into a corner there, so let me grab this and move it over here. All right. So then minus 1 times 2 is 2. So we'll end up with lambda squared minus 3 lambda plus 2 minus 2. And it's supposed to equal 0 at the end. Cancel those 2's out there, and you can see that you can factor that into lambda and lambda, minus 3 equals 0. So lambda equals 0 or lambda equals 3, okay? So those are the two values that you got for lambda. And so let's see, can I rearrange this stuff slightly so that, just trying to make a little bit more room here. And so, yep, that's not gonna get any better. All right, so, and just move these over to here. All right, that should be good enough. All right, so maybe I'll slim down what I'm writing. So the thing you're going to have to do is to actually write your A minus lambda I and multiply it by the x vector. So let's go ahead and do that. And I'm going to start with lambda equals 0, okay? So I'm just going to take A minus, and on the diagonal, I'm going to subtract 0. So that just means 1, 1, 2, 2. And then I'm going to write x1, x2 here. And that needs to turn out to be 0, 0. So when you dot there, you'll see x1 plus x2 needs to be 0. And when you do it on the second row, you get 2 times the same thing. And if you go ahead and do your substituting sort of thing, you see that x1 needs to be equal to negative x2. Now, this part is going to feel like cheating. I'm going to make my x vector be equal to, and I choose a value for one of those, okay? my favorite choice in the world is to choose 0. But if I do that, this turns into 0, 0, and you can't have that. So instead, I'm going to choose my x2 to be 1, and so my x1 has to be -1. As you can see up there at the top, I had those reversed when I did it last time, but notice they're just multiples of each other, so it's fine. You could have also had 2, -2. That would have been fine as well, all right? So then we'll do lambda equals 3. And so for that, just take the same a that you had before and subtract 3 from each of the diagonal entries. So 1 minus 3 is -2. We got a 1 here, a 2 here, and then a 2 minus 2 is 0. I said, what the hell did I just say? 2 minus 3, sorry, is going to be -1. So when we have that times x1, x2, by the way, if you don't like subscripts, you can call those a and b or whatever you feel like. But now we will have -2 x1 plus x2 equals 0. And notice that if we do the other one, it's really the same thing, okay? So I'm just going to go ahead here and say that my x2 needs to be 2 times my x1, and that's going to motivate me to choose my x and have the x1 be 1, so that the x2 is 2, all right? Again, if I had the choice to make something 0, I would, but I don't, so I just choose the easiest thing possible, 1, maybe -1 if you have a couple choices to make. So that means that your eigenpairs here end up being something that you can group together, right? So let's shoot for a 3x3 example, all right? So with our 3x3 example, we're going to start right off with the determinant part. So 2 minus lambda, I'll put a 1 and a 1 here, and a 2 and a 1 minus lambda there, and a 1, and a 0, and a 2, and a 2 minus lambda, okay? All right, now we need to expand that determinant out. Now, I've really not had y'all do much with that. I've always had you expand across the top. If you wanted to expand across a different row, you can. And you just have to remember upper left is plus, and it alternates as it goes along rows and columns. So for this here, we're going to take that determinant and have 2 minus lambda times, and then I'm going to block off this column and row and see what I have left. I would have 1 minus lambda, 2, 1, 2 minus lambda, and then minus 2 times, and I block off the row and the column that's in. And once again, I have jammed things up a little bit, so I am going to take and drag them over here, except it grabbed my straight line. Okay. So 2 times the absolute value. Oh, what was that? Block out this row, block out this column. 1, 2, 1, 2 minus lambda. Okay. 1, 2, 1, 2 minus lambda. All right. So that's going to have 2 minus lambda times 1 minus lambda, 2 minus lambda, minus 2, minus 2 times 2 minus lambda minus 2. Okay, so 2 minus lambda times lambda squared, let's see, minus 2 and minus 1, so minus 3 lambda, plus 2 minus 2, minus, and it looks like those 2's are going to cancel, so really plus 2 lambda. Boy, this looks pretty icky, doesn't it? Oh, look, those canceled as well. So now I have 2 minus lambda times lambda squared minus 3 lambda, and then plus 2 lambda. Okay, so an important lesson comes out here. Can you see that there's a factor of lambda to the whole thing? If you can spot a factor, pull it out, because the factoring gets to be super nasty if you don't. All right, I see the lambda there, and so that means remaining, I'll have to say 2 minus lambda, and then times lambda minus 3, and then plus 2. Okay, so lambda times, all right, 2 lambda minus 6 minus lambda squared plus 3 lambda plus 2. Oh, that's a mess. So lambda times minus lambda squared plus 5 lambda, and then is it minus 4? Okay, it would be super handy to take a minus out of that so that I can spot how to do lambda squared minus 5 lambda plus 4. And so we will have minus lambda times lambda minus 4 lambda minus 1. Okay, so what was really important out of that was to get down to the factored part. Okay, so for the sake of room here, I am going to take just that bit. Wow, it is erasing in a super weird way. Okay, I think it's because I just had so much written there. So when we set that equal to 0, we'll get lambda equals 0, lambda equal 4, and lambda equal 1. Boom, 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 one after the other. All right, so I'm going to take lambda equals 0 and think about 2, 2, 0, 1, 1, 2, 1, 1, 2, and my x1, x2, x3. Okay, across the top, 0, across the top, when you dot that out, you will end up with 2x1 plus 2x2 equals 0. So x1 equals negative x2. And then the next row, you will have x1 plus x2 plus 2x3 is equal to 0. And that tells you that your, gosh, I guess your x1, no. We want to maybe solve for just one of these. Let's say x1 equals minus x2 minus 2x3. Okay, so because of the fact that we know that x1 has got to be equal to the negative of x2, let's alter that a little bit. Oh, right. Let's just change that, change what we approached with that, and let's just spot that since x1 plus x2 has to be equal to 0, our x3, it turns out, has to be 0. Okay? So that tells us that our x vector we've got here has to have a 0 in the third component, and then the x1 and x2 have to be opposites. So maybe negative 1, 1. Okay? So that's going to be the eigenpair that we'll keep track of there. Okay? And I am going to tidy this up a little bit here and just write down x1 plus x2 plus x3, nope, 2x3 equals 0. All right. So now we're going to try the next one, which was lambda equal what? 4. Right. Take the matrix, subtract 4 off the diagonal. So negative 2, 2, 0, 1. What did I say here? Minus 4, so negative 3, and 2, 1, 1, and negative 2. Okay. That seems a little bit discouraging because with what you're doing here, it's going to look like you've got 3 linearly independent equations that you're working with. But what we will find out is that if we solve just 2 of them, that the third one will actually end up being a combination of it. So we're going to have here that x1 and x2 have got to be equal. And then we're going to have x1 minus 3x2 plus 2x3 equals 0. And so if we go ahead and solve for x3, we can see that it's going to be 3x2 minus x1 over 2. Yuck. That seems a little bit miserable there. But if we choose a value for our x1, it's going to tell us what our x2 has to be. And that then will tell us what their x3 has to be. So I'm going to come along here and choose my x1 to be 1. And then I know that my x2 has to be 1. And then 3 minus 1 over 2. So that's 2 over 2 is 1. So it looks like the vector we're getting is 1, 1, 1. Okay? All right. And if you go ahead and check there, then x1 plus x2 minus 2x3 is going to be 1 plus 1 minus 2 equals 0. So it does, in fact, check. So I'm going to not bother with that just because I need the room here. All right. So the last one we have, lambda equal what? 1. And so for that, we're subtracting 1 from the diagonal. So we have 1, 2, 0, 1, 0, 2, and 1, 1, 1. Okay. So you multiply that by x1, x2, x3, and set it equal to 0, 0, 0. You should have your x1 plus 2x2 equals 0, and your x1 plus 2x3 equals 0. So your x1, well, that makes this a little bit more puzzling, right? We can see that both x2 and x3 are linked to x1. So I'm going to go ahead and say my x2 is going to be equal to my x3, which is going to be negative 1/2 of x1. So when I'm choosing my x here, I am going to choose an x1 that makes that convenient, and I'm going to choose it to be 2. And then the other 2 will be negative 1 and negative 1. Okay. All right. So that means we've got the 3 here, and I'm going to make use of those in a later example. So bear in mind that we have done those. But also keep in mind that if I had taken the negative of one of those, it would have been fine. Okay. All right. So here's one where we get complex eigenvalues. I've already written down the solution there, and that is because I'm worried that I'll mess it up. So let's write down 2 minus lambda minus 1, 2, and then minus lambda. And so that means that you will have minus lambda times 2 minus lambda, and then minus a negative 2. So that means you will end up with lambda squared minus 2 lambda plus 2. So if you set that equal to 0, you can either figure that out by doing the quadratic formula or by completing the square. I prefer completing the square, but I know not everybody else does. So let's see, negative b plus or minus the square root b squared minus 4a and c. And that's all divided by 2 times the a. So we have 2 plus or minus the square root of, let's see, negative 4. Oh no, fear, loathing. We're going to end up with 1 plus or minus 2i for our solution there. Okay? So we're going to deal with one of them, and we're going to have a nice effect here. Okay? Let me use just a little bit of language here. If you have a complex number 1 plus 2i, and I write that bar over it, we refer to that as taking the conjugate. And all that means is to change the sign of the imaginary part, not the real part, just the imaginary part. Okay? So the roots to quadratic equations come in conjugate pairs. So when you get them, one of the nice effects that comes in there is that your conjugate pairs, when you look at the eigenvector that goes with the eigenvalue, they'll also be conjugate pairs. So I'm going to jot down here lambda equals 1 plus 2i. Okay? And we're going to work this out. So we're going to take and subtract 1 plus 2i from the diagonal. So 2 minus 1 is 1, and then minus the 2i. If that'll make it a little bit miserable. We're not going to do anything to this 2. We're not going to do anything to this 1. But we're going to take and subtract the 1 and subtract the 2i here. Okay? And now we're going to have x1 and x2 equal 0, 0. So remember on my previous example that I said when you have multiple equations that you're dealing with, you are going to end up having a choice somewhere on them. So for this, if I go ahead and say 1 minus 2i x1 minus x2 equals 0, I don't need to write the second equation down. It's going to turn out to be a multiple of the first equation. So I am going to just go ahead and say x2 is 1 minus 2i x1. Okay? So that if I choose my my x1 to be 1, then my x2 has to be 1 minus 2i. Okay? So that is the eigenpair there. And for the eigenvalue 1 minus 2i, the eigenvector that is going to go with it is going to be the conjugate of that eigenvector there. So it'll have a 1. Remember that when you change the sign of 0i, it's not going to change it. And 1 plus 2i, because we're just changing the sign of the imaginary part. Okay? So for complex eigenvalues and complex eigenvectors, you're going to have them coming in conjugate pairs. All right? Our actual usage that we will put complex eigenvalues to, you won't have to run into that portion of things quite so much. Okay? All right. Let's see what we can do on this example here. Man, this looks intimidating, doesn't it? Gosh, sure would be nice if I don't know, I had a computer or something. I wonder, is there a computer lurking around here somewhere? Oh, 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 you found out my secret that I didn't actually know how to translate that on my own. Man. But, oh, look at that. There's Colab. And my friendly neighborhood Colab, I have been doing all kinds of little things in here. If you hit Command MB, it will create a new cell for you. And one of the things I've been using a lot in these is this feature here. If I just go in and say to it, oh, maybe I should blow that up a little bit so you can see it a little better, that my matrix is going to be, what was that? 4/5. That would be 0.8, negative 3/5, negative 0.6, 0, next line, 0.6, comma, 0.8, comma, 0, next line, 1, 2, 2, oops, close. All right. So that's how you define a matrix object. Notice it didn't print it out for me there. So I'm going to purposely tell it to just print A here and make sure that it printed it nicely. So is that what I had? And yep, looks right to me. So now instead of that, I am going to have my eigenvalues. Let's see, I can't, by the way, I've said this somewhere else. Turns out lambda is a reserve value, a keyword. I can't actually use it. So I'm going to just use capital L for lambda. And then the eigenvalues, I'm going to put them in a matrix called P. And I am going to say eig A. And then down here in the print statement, I'm going to ask it to just print my L for me. Okay, boom. So nicely enough, I was able to get the eigenvalues there. But it should confuse you just a little bit if you haven't dealt with physicists before. It says J, not I. What the heck? I and J, they're kind of the same letter. I mean, you know, in the Latin alphabet, that was a punchline from an old movie. But yeah, J is just the other abbreviation for I. So when we need to know what those eigenvalues are, we're going to have one of them here being lambda equals 2, one of them being 4/5 plus 3/5 I, and the conjugate value there, 4/5 minus 0.6. Okay. Now, for that matter, you might say to me, hey, Ben, why don't you just give me the eigenvectors? Because those are going to be stored under the P. Maybe they'll be right, maybe they won't. Okay. I am going to insert an extra line here and tell it to print, what was it, L, and then I'm going to tell it to put a couple of blank lines, right? So now you can see the eigenvalues and the eigenvectors, and it lines them up here, okay? I've got my iPad here and I'm jotting these down. Lambda equals 2. The eigenvector that goes with that, it said is 0, 0, 1. That's good enough to deal with. That's not too bad. Then the one for the first complex one looks horrifying. Why does it look horrifying? Well, if you'll notice here, this number, 0.7624, it's about twice what this is. I'll bet there's actually a relationship going on there. And then that appears here in this other place. So, but this part here ends up being just a real number because the imaginary part is going out there. But okay, we kind of need to see how to get those because the computer has not failed us. It's just chosen a multiple that is super messy. You and I don't look at that and say, oh, that's this fraction. But the computer, everything's an approximation. So it's thinks that's good enough. Okay. So what we're going to do is to tackle just going ahead and figuring this out. And so let me share my screen. Cross your fingers, please. All right. It's decided to play ball. All right. So I'm going to take here and subtract that lambda from my main diagonal here. So 4/5 minus the 4/5, so I've got a 0 real part, and then minus the negative 3/5. So I'll have 3/5 I. Okay. Then the negative 3/5 and the 0 we don't need to do anything with. Then I've got a 3/5 here, and now I've got 4/5 minus 4/5, so the real part goes away, minus a negative, so now it becomes positive 3/5 I, and then a 0. And then down here, I've got a 1, I've got a 2, and oh my God. 2 minus 4/5 will be 6/5, and then minus a negative, so it becomes plus 3/5 I. Okay. X1, X2, X3. And that needs to turn out to give us 0, 0, 0. So here's hoping, all right? So we're going to have that 3/5 I, X1, minus 3/5 X2, and then 0 X3s needs to then give us 0. So that says that X2 needs to be equal to I times X1. Does that make sense? I just went ahead and added to the other side and canceled out the 3/5 sign. Okay. Then if we go ahead and multiply the next one down there, we would have 3/5 X1 plus 3/5 X2. Oh, I messed that one up, didn't I? 3/5 I X2 needs to be equal to 0. And so that looks pretty similar there. You would have your X1 would need to be equal to negative I times your X2. And if you're saying, I don't know if, that seem like different things to me. Well, this one really is X1 equals 1 over I X2. If you know your powers of I, those are really the same thing, okay? So we actually have then the same equation in the first and second rows. So let's just leave that at that. And let's look at the last row, which says X1 plus 2X2 plus, yuck, 6/5 plus 3/5 I X3 needs to be equal to 0, okay? So we know that X2 has got to be I times X1. Let's substitute that in there and have X1 plus 2I X1 plus the 6/5 plus 3/5 I close X3 equals 0, okay? So you can see that we have 1 plus 2i x1 and plus, now this is all messy and stuff. Can I just take out 3/5 and say 2 plus I x3 equals 0? If I'm not real fond of this, but let's say x3 equals the 1 plus 2i divided by the 3/5 2 plus I, and then the x1. So that's a mess, right? But this this bit right here before the x1, I'm going to copy that and paste it over here. And we're just going to tidy that up real quick and then we'll replace it. So if you've dealt with complex numbers before, you know to get them out of the denominator, you multiply by their conjugate in both numerator and denominator. So that means that you have 3/5 times. When you multiply conjugates together, you just square the real part plus square the imaginary part. Okay, so that means we're going to have a 5 there. That's going to be nice. All right. Upstairs in the numerator, things are not quite as nice because as we're doing this, we have to go ahead and multiply out. And so we'll have 2, and then let's see, 4i, and then minus I, so plus 3i. And then you have to think with foiling these out that we've got a minus 2i squared. So minus 2i squared is really plus 2. So you have 4 plus 3i divided by the cancellation down here gets you 3. Okay, so that means you have 4/3 plus I. All right, and that looks a little bit messy still, but it's better than what we had before. And so I'm going to just take that part, toss it out, and grab this part. Oops, grab this part and move it over there. And that should do that. All right. So that says that for the lambda equals 4/5 minus 3/5 I, you get an x that's going to be, we get to choose x1, and then x2 has to be I times that. And then x3 is going to be 4/3 plus I. If you'd really like that to look prettier, you might change your mind after a while and say, I would like to choose my x1 to be 3 and have 3i for the x2. That's not too bad. But when I multiply it over here by that 4/3, I end up with 4 plus 3i. And then for lambda equals 4/5 plus 3/5 I, the eigenvector you would get is going to be 3 minus 3i, 4 minus 3i. Okay, so complex eigenvalues come with complex eigenvectors. The complex conjugates then match up. Okay. All right. So our next bit is this super, super neat thing that if you have a matrix A, and if you know what the eigenvalues and eigenvectors are for it, you can take a matrix of the eigenvectors, and actually I'm going to have to turn to another page and make sure I get the order right there. It's either PA, P inverse, or the reverse of that will get you the diagonal, okay? Let me see, I wrote it, I believe, here on the next page. Yeah, here we go. P inverse AP will get you the diagonal, all right? So that means that I should have put my inverse symbol. Nope. Come on, dude. Don't be sloppy like that. So I should put my inverse symbol over there. And now all fixed. So the thing that we have to do, though, is to get the eigenvalues and eigenvectors for A. P is going to be the matrix of the eigenvectors, and D is going to be the eigenvalues. Okay? Little thing, you have to have linearly independent eigenvectors to make this work. The eigenvalues can be repeated, but the eigenvectors have to be linearly independent. So sometimes that gets us into a little bit of trouble. All right, so that means we want to know what the eigenvalues are for this matrix here. Gosh, could I? Let's see. So I'm going to come over here, and I am just going to put my matrix back in there. And it was 3, 2 on the top row, -2, -1 on the bottom row. And I'm going to tell it to just print this out for me. Oh no, did you see what happened here? It's the way the computer works, it's all an approximation scheme. Something in its round off went a little bit wrong. But the problem was set up in such a way we should be getting 1 out of both of these, okay? So let's take a look at what's going to happen with that. And we are going to be in the weird situation that the diagonalization is going to take it down to the matrix. I believe it's going to be 1, 1. What was that? We'll check and see. All right. But we will go ahead and do this part by hand because the answers that we got there were not super obvious about what was going on. So, oops, I should have written down that lambda equals 1. We are going to come along here, and we're going to subtract 1. And so we'll have 2, and that one gets left alone, and it's -2, and that one gets, we have to subtract 1 from it, so -2. So x1, x2, and this is equal to 0, 0. And so that is going to mean that we have x1 plus x2 equals 0, and the other being the multiple, or the other one being just the opposite of that. I didn't write my 2's, sorry. -x2. And so for this, the eigenvector, we get to choose one of them. I'm going to choose x2 to be 1, and x1 will be -1. Okay, so let me jump across there and see what I had. And then I can't finish this. The reason I can't finish this is that I only have one possibility for my eigenvector, right? Dang it. Sorry. So this is an example I can't finish. I should have worked it out ahead of time. But somebody was saying that they wanted to see me work these out, you know, to see my thought process. Unfortunately, my thought process is sometimes just wrong. Yeah. Okay, the next one I worked out ahead of time. The reason I worked it out is you'll see. So jumping back across here to the iPad. All right, so this one we've got a 3x3 example that we're going to diagonalize, and we already figured out what the eigenvalues and eigenvectors were for it. Okay, so we get this 3x3 matrix, and we go figure out the eigenvalues, eigenvectors, either using the computer or else by doing things by hand with solving a polynomial. But one way or another, we get the eigenvalues, and I happen to be dealing with them in the order 1, 4, 0. If you want to flip them in a different order, you can totally do that, okay? But you have to have the eigenvectors that go with the eigenvalue in that same order, right? So once you have that idea in mind, we're going to make a matrix P, which is just made up of those eigenvectors, okay? The D that we're going to end up getting out of it should be in the same order as the eigenvectors. Unfortunately, we need the inverse of that matrix there. So, oops, I'm starting to do something else, and I forgot I had to stop sharing in order to share the different thing and come over here. And so for this matrix, I think it's almost the same matrix that I'm going to work with here. Not quite. 2, 2, 0, 1, 1, 2, 1, 1, 2. Okay. So I'm going to, comma 2. Okay. I am going to input that as my matrix P, and there's that matrix constructor has this nice feature to it that you just say P dot I. I don't like that notation, but P dot I, it will give you the inverse of your matrix. So boom, uh-oh. It did not like that. What did it not like? Let me see here. P is a matrix. Okay, P dot I. Language error. P dot I, raise language error, singular. It says that was a singular matrix. Oh no. Well, if that's a singular matrix, did I mess something up earlier? Oh, I'm sorry, folks. 220, 112, 112. Well, yeah, hell yes, that's a singular matrix. And but that's the A. Ah, come on, dude. You're just a goof. That was supposed to be -2, 1, 1. This is probably what I had input earlier. 1, 1, -1, and then 1, 1, 0. 0. Okay. And it's saying that that is a singular matrix. And it can't be a singular matrix because I had it earlier. This is one of the travails of working in a room by myself. All right. I just didn't see my comments there. So hopefully everybody recognizes 0.3 repeating as 1/3, 0.6 repeating as 2/3, and -1 is -1. Haha. So that is where I ended up getting my P inverse from. Sorry, I don't do everything by hand, but you know, I know you would prefer to get those artisan handcrafted inverse matrices, but yeah, unfortunately, I'm just mass producing them with old Python. I really should have worked out something with a matrix P and A so it would be IPA, because yeah, I know. All right, so down here below, I wanted to go ahead and by hand work this multiplication out. If you're not really interested in that, you could skip ahead a little bit in the video. But so I'm just going to copy down this part in hopes that it gets nicer as we go along. And I'm going to go ahead and multiply these two matrices here. And when I do that, I'm going to have to talk about this first row, and I'm going to dot it with each column as we go. So dotting that, we end up with a -4 plus 2 plus 0. So -4 plus 2 is -2. And then when we dot the next one, we should get 4. And when we dot the next one, we should get 0. All right. And then we're going to come back and do the second row, the 1, 1, 2. And so you get -2 plus 1 is -1, and then plus 2, so +1. And then the 1, 1, 1, so you should get 4 of that. And the 1, -1, 0, you should get 0 out of that. And since the next row is the same, you better get the same thing. And then we have to come along here and we'll dot this row. Just remember, everything has a third in it. So I'm going to take and say -2 times the -1/3, so +2/3, and then -1/3. Oh God, 2/3 minus 1/3, and then +2/3. So that says that you're going to get a 1 out of that, right? Then when I do the 4, 4, 4 here, that's just going to add those things up. And so when you add those up, you end up getting 0 times 4. And then the 0, 0, 0 will get you that 0 there. And then we'll come along here and we have 1/3, 1/3, 1/3. So it's basically going to add things up and divide by 3. And when you do that for the first column, it adds up to 0. And that divided by 3 is still 0. And then the 4, 4, 4, when you add those up, you would have 4/3 plus 4/3 plus 4/3. So that's going to end up with a 4. And then the bottom row, when you dot it along, you just have to subtract the second element from the third element. So we end up saying 1 minus 1 is 0. And then for the 4, 4, 4, you end up having just 4 minus 4 is 0. And then the 0, 0, 0 dotted with anything is the 0. And so that is, in fact, the diagonal matrix that I've been saying something about up here. So this is a super handy thing because some of the calculations that we do, we want to get maybe a fairly large power of a matrix, maybe even an infinite power and a summation. Okay, so in order to see that work out, let's take a look here. And I'm sorry to disappoint you. I have worked it all out in advance because it is super tedious and super easy to drop a negative and stuff like that. So this power example, we've got a matrix A that we're working with. We're being asked to get the third power of it. Yes, you could just say, hey, computer, get the third power. And the computer will do it faster than I will do this, certainly. But there's something we're going to do in a minute where it would be handy to know how to do this. So immediately I go and find out those eigenvalues. I can go find them out by hand, or I can find them out by just asking the computer to do that, okay? But if I am, in fact, doing that, say I'm doing it with lambda equals 1, I subtract 1 from the diagonal, and then I have to solve b minus c being 0 and a plus c being 0, and then this thing here, which will turn out to be a multiple of those. So because we've done that sort of example earlier, I'm not going to work through all the painful details of that. I am just going to say, yeah, as a matter of fact, I'm going to even do away with this bit here. And I am just going to say, all right, we know Lambda equals 1 gets us this. Lambda equals 3 gets us this one. And lambda equals 2 gets us this one. So if we take the P and just for that, just list those eigenvectors in the order that we got them in and take and find the inverse of it. I again cheated and went to the computer and asked it what the inverse was. Yes, you can do that too, okay? But the calculation thing that we're going to be interested in is going to have to do with this right here. If A is going to be equal to the, if we can write A as P times the diagonal times P inverse, then when we know that, if somebody asks us to calculate A cubed, and I have to undo that because that is sloppy. Okay. If somebody asks us to calculate A cubed, then we can say that that's going to be PD P inverse cubed, which means that we could just take and write each one of those out separately. And notice that the P inverse and the P's that are next to each other cancel out. And that means that we are really going to end up talking about P times D cubed. And cubing a diagonal matrix, you just cube the entries, okay? So that means that for this thing that we're trying to multiply out, that we can just take the P that we already know about, the cube of the diagonal, so we have to keep them in the right order, 1, what was it, 1, 3, 2, and so when you cube those, 1, 27, 8, and then times the P inverse, and when you calculate all those out, you will end up with this 1, 7, -7, etc., etc. Okay, so turns out this is pretty doable, and you can do this even for very large values, for very large powers. So calculating the powers of matrices is not terribly onerous. This is a pain. So we want to think about getting the exponential of a matrix. And I need to add an extra page here because to get the exponential of a matrix, you're going to have to remember this, that when we talked about e to the x can be written as a summation 0 to infinity x to the n divided by n factorial, okay? So that means that you can evaluate your exponentials kind of like polynomials, but man, you don't really want to do it that way, right? But we can at least define it that way. So if we want to take a matrix and put it to a power, remember that we will say P, D, P inverse. Did I get that in the right order? So what was it? P, D, I don't know, P, D, P inverse, right? Okay. And then put that to the nth power. But we just saw what happens on that is P, D to the n, P inverse, right? So if I divide that by n factorial, that means I'm just dividing those diagonal entries by n factorial. And if I'm doing a summation from 0 to infinity, a to the n over n factorial, then I will have, I started to put my summation out front, but I will have something like pi, because that'll be a to the 0 power, p inverse plus p a over 1 factorial p inverse plus p a squared over 2 factorial p inverse plus dot dot dot. Hey, look at that. All of those have a first factor of p. And all of them have an n factor of p inverse. So that means I am not going to re-record this whole damn video just because I have a stupid typo in this step here. Sorry, folks. That was supposed to say d. So d squared, d squared. So that is going to actually be e to the d p inverse. And e to the d is literally just going to be exponentiate the diagonal. Okay. So turning back here to see what it was we did, we started out with a matrix that was this here, the 2, 1, 0, negative 1. And we went ahead and found out the eigenvalues were going to turn out to be 2 and negative 1. And so I went ahead and showed the actual steps here in trying to find the eigenvectors. And I did not need to do that because y'all were already experts. So come on, you. So I'm going to just move this over here. And I'm going to clear this a little bit out. And I'm going to take this guy here and move it above that. And move this over here and say that is the x that goes with that. And so the p that we're going to think about here, how do I have that written here? Sorry, folks, that was a little bit of a mess. All right. So this is the p that we're referring to, and this is the d, the diagonal matrix, and this is the p inverse. And we can see that when we multiply that back together, we would actually go ahead and get the a, right? And so consequently, if you can do that, then assuredly, you could also, and that's supposed to happen, you could also get powers of a, right? And if you're going to do summations, you can bring summations inside, and that means that we can get this with simply the p, the e to the d, and the p inverse, and you just multiply out a matrix there, okay? This might be a little bit too much for your collab to actually do the whole calculation there for you, because with the exponentials, it will want to approximate them. But otherwise, it's something that's fairly doable, okay? You got to find the eigenvalues and eigenvectors. You kind of pull stuff apart there, and you exponentiate in the middle. You just have to keep track of stuff. Okay. So the homework assignment you're about to do that has all that sort of stuff in it, it's a little bit cumbersome. Okay. Do show me that you can do one of the eigenvalue eigenvector problems totally by hand. Okay. Check it to make sure you get the right answer. Check it using the stuff that I've shown you here on Colab. After you've shown me that you can do it, then as you go through with these, it's okay to get the eigenvalues with the computer. The eigenvectors, don't give me those decimal approximation crap, okay? But you should be able to spot things like, oh, it said 0.7071 here and 0.7071 here, so those two things need to be equal. You know, there's stuff like that that you can figure out and put together. Your eigenvectors need to be nice. Don't give me decimal approximation crap when you can get nice numbers, okay? So if you can't spot the nice numbers out of what's appearing on the screen from Colab, you have to do it by hand, okay? But I'm not giving you super big ones. I think that this is a set of stuff that you should be able to get done in 2 hours, okay? If not, finish it up tonight and get it turned in, okay? All right, I'm gonna let you go. Talk to you later, and have fun. I had that. No, don't have fun. Just talk to you later.